according to my watch, it's now 9 o'clock, which means it's time for us to get going. On the agenda today, just one topic, digital filtering. And this is pulled primarily from section 9.4, which is not titled digital filtering. It's entitled enhancing digital signals or some such nonsense. But really, it's centered on digital filtering and why and how we do it. And so thought I'd start with a bit of a motivation. Here's a problem. This is a problem that, this is a real life problem that I experienced as a postdoc. It actually wasn't my instrument, but I was right next to the person who was contending with this issue. So this was this is voltage versus time, a measurement of a detector. And then the signal went up, but there's a lot of noise. And the problem was, well, the question is this. Is it better to sample at the maximum bandwidth of your electronics, which was shown and illustrated here, or to sample at the bandwidth of your signal, which is not necessarily matched to the bandwidth of the electronics? Now, if you were to sample, I'll change my color here, sample with respect to the bandwidth of the signal, you can see the signal has sort of a rolling feature underlying it, then you might, sample less frequently. Does that give you a signal-to-noise advantage? Maybe you can see it how it's illustrated. It really doesn't, right? All you're doing is actually making it worse. You're sampling fewer data points with the same noise, even though your signal has a much more rolling features, has more rolling features associated with it than the sampling frequency in which you're recording it. Why is this a common problem? Well, I mean, it's, we have high-speed electronics. A digital oscilloscope can sample very quickly. Why not run it at full capacity, irrespective of the bandwidth of your signal? So the answer is there's really no reason not to sample at the full bandwidth of the electronics, because there's no signal-to-noise advantage to undersampling if you're not doing something to affect the bandwidth. Okay, I'll write that down here. No advantage. No advantage to sampling at any frequency below the bandwidth of the electronics. And that is generally true. So there's two things you can do. Route one, change the bandwidth in the electronics. For example, putting in an analog band pass filter or any bandwidth limiting electronics, an RC filter. How many of you talked about RC filters in 620? None of you. Huh? One person talked about RC filters in 620. Was it covered as a topic? Okay. Okay. Briefly. We're going to cover it briefly here too. So that's one route. In other words, if you put in something that limited the bandwidth in your electronics, then it would be effectively reducing, for example, if you had high-frequency noise, as in the present case, and a low-frequency signal, if you put in something that suppresses high frequencies and passes low frequencies, then you will automatically suppress this high-frequency noise that you see. And in that case, when you digitize, you can sample at a lower frequency, and you'll be just fine, because the signal itself will already have been preconditioned to remove the high-frequency noise. That's one route. However, the route with greater flexibility, arguably, is post-processing. And it's arguably the greatest flexibility because it requires absolutely zero changes to the measurements. It only affects how you subsequently treat the data. And that's what we're going to be focusing on right now. So what ideas, without knowing anything about digital filtering or anything, just intuitively, if you looked and made this measurement, what would be the first thing you'd be likely to try to reduce the noise from that red trace, the original red trace? Average, right? There's two obvious ways of doing it. The first way is binning, right? Every 5 data points, just turn that into 1 data point. Another way is every pixel, just write the average of 5 and then move that 5-element average across the data. So we'll talk about route 1 here. For digital signal processing, we'll start with the running average versus binning. So if we bin, then we take those data. Binning is combining. The binning is combining and reducing the data length proportionally. Hopefully I don't need to describe binning. The running average is a little more interesting. So we'll really focus most of our attention on that because the running average does not significantly affect the overall number of data points in the processed result. So for the running average, the total number of data points is similar to the starting number. So if I've got, so how does this work? Let's say I'm considering the 13th data point and with a 5-element average. Then what am I doing? I'm taking the output, the smooth. Oh, come on. We'll call it D prime 13 is 1/5 the sum of 11 through 15. Does that make sense? So we're just replacing that 13th element, the middle of this running average. We're replacing it with the average of the 5 data points in its neighborhood. And then we move over to the 15th, and we take this little box, and we keep sliding it along. Does that make sense? So if we think of the data, got a little carried away there. If we think of the data, something that goes in time, what we're doing is building our little digital filter and convolving it with the data trace. Because what are you doing in a convolution? Well, you're taking the filter and you're sliding it across. You're taking one function and you're sliding it across the other function, right? And you're integrating over that value as you slide. Well, that integration numerically corresponds to summation for discrete values. So that's the summation is equivalent to the integration that we consider when we do convolution. So this really is actually convolution of the data with a rectangular filter. Why do I call it rectangular? Oh, there's a question first. Yes?
What would happen if you have data that is more than one image? So if you have like an image pixel, what if you want to average
an area?
Yeah.
Yeah, so the question is if you have a two-dimensional data set, think an image or think GCMS. GC on one axis, MS on the other axis. Two-dimensional data set. How do you do digital signal processing on something like that, where you have a separate filtering operation along each individual axis, for example? In an image, it's even easier, because then you'd have instead of a one-dimensional line, you'd have a two-dimensional image that you would convolve your other image with. And that image would really be much smaller, just like this is a much smaller rectangle than the size of the image I'm trying to, the data image, or the data trace. But it's analogous. It's exactly analogous. It's just extension of this idea from one dimension to multiple dimensions. Okay, and I've lost my train of thought. Why do I call it a rectangular filter?
Because it's one dimension and there's 5 entries for this. So technically, in terms of the architecture of the filter itself, it's longer in one axis than the other.
So it has something to do with the geometry of the filter. I agree. Yeah.
you're only looking at 5 data points, and then everything else is going to be 0, and then you have the amplitude of 1/5.
Yeah, if I look at what this digital filter looks like, it's 0 everywhere. At the origin, it's 1/5, and it's 1/5 all the way out here. Right? So that's why it's called a rectangle, because it actually literally is a rectangular function that I'm convolving the data with. Let me point out another couple interesting things. If I am convolving the data in this way with this running average, what do I do about the first and second data point and the last and second to last data points? I have a problem there, right? What's my problem? Well, I shouldn't ask that question. I might get a whole suite of different answers. What is the problem? Let me be more specific. What is the problem with trying to apply the rectangular digital filter for the very first data set? Yeah?
You don't have the 2 data points to the left and the 2 data points to the right for the average.
Yeah, I can't apply it when these don't exist and when these don't exist. So, a couple of notes. One, digital filtering is a convolution. In time. I put time in quotes. And I put time in quotes because we will treat it as time even though the x-axis could be anything. But it's just intuitive to think in terms of time and frequency as opposed to distance and wave number, for example. So that's my first point, convolution in time. The first and last sections of the data of the convolved data of the smooth data, and I'll use smooth as the output, whether it's smoothed or not. You can put in a high-pass filter that will retain all the high-frequency things that will not smooth an output much at all, but if it's processed, I'm going to call it smoothed, just to be consistent with the notation in the lecture notes as well. Okay. The smoothed output is slightly shorter because of the problem with the ends. let's see. Okay, so the smoothed output is slightly shorter by a length of f, half on the front end, half on the back end, because of the problems with the start and stop. And f, consistent with the lecture notes, is 1 less than the length of the filter. And that sounds like, why would you do that? Why not have f be equal to the length of the filter? It's because we go from negative f over 2 to f over 2 with 0 in the middle. So f must be an even number. Makes it much easier in terms of coding than to have f be an odd number and subtract 1 and have that whole thing. So it's just convenience. F is, the filter is always 1 greater than the length of f. But we lose 1/2 of f on one side, a little less than 1/2, and a little less than 1/2 on the other side as well. That's a fact of life. It's part of the cost of doing business with digital filtering. The solution is to just acquire a longer data set, either before or after. Make sure you have plenty of data before something interesting happens, and continue to acquire data long after something happens, and you have plenty of opportunity for throwing those data points away throughout the digital signal processing. Okay, the third is that the running average is a rectangle. Why is that significant? Why would the Fourier transforms be relevant? It's a very good question. This must relate to Fourier transforms because that's a topic we just finished as a prelude to digital filtering. What is the Fourier transform of a rectangle? They all cry in unison? Sync. Excellent. So if I'm doing a convolution with a rectangle in time, I'm doing multiplication by a sync in frequency. Is that what I want to be doing? I mean, I don't know. The question is, how do we decide? If there's really no reason we have to stick with this running average as the only operation we choose to do signal processing by convolution. That's the key point. I'll say that again, because it's sort of a key point. We are not limited to the rectangle as a convolving option. We can be more creative. Why would we want to be? What's the primary purpose of this course? Yay! Signal to noise enhancement. Why would we want to be more creative than a rectangle in terms of our convolution? The answer, there is only one answer, right? Signal to noise enhancement. Why would we conceive of a scenario where convolution with something other than a rectangle might improve the signal to noise? Well, there's only one way to really answer that, and that's to ask yourself, what does the signal look like? What does the noise look like? How might I maximize signal to noise? And this pondering is best done in the frequency domain. Okay. Signals and noise. Signals and noise both live in the frequency domain. So the general strategy is to ask yourself, what is the frequency content of the signal? And equally importantly, because it's a ratio, what is the frequency content of the noise? And then what frequency domain product would increase signal to noise? And then what's the last step? Well, not the last step. The next step, Fourier transform. And convolve in time. And convolve in time means perform digital filtering. There's a question.
Is there any reason that we couldn't just switch the last two steps to multiply in frequency, then Fourier transform to get our time signal back?
So the question is, if you're understanding everything in the frequency domain, why not do the multiplication in the frequency domain and then Fourier transform? The answer is it loosely is equivalent. The advantage of doing digital filtering is that the vectors that you're multiplying don't have to be the same length. In other words, I can have a 5-element filter and a 10,000 element data set, and I have no problem digital filtering, but doing the Fourier transforming and multiplying is a little more inconvenient. But in principle, you absolutely can do either one of these. In practice, there are advantages for doing digital filtering when your filter is small relative to the data set. Excellent question. Okay. Let's do an example. Let's say I have my rolling average, and I wanted to remove the DC, remove the zero frequency content in a rolling average. What's that going to look like? Example. I'll call it a running average, because that's what the lecture notes call it. A running average modified So what would that look like? Well, if I take my rectangle and with a width of 5 for a 5-element digital filter and an amplitude of 1/5 because it's normalized. And if I Fourier transform this, what do I get? Gives me a sink. In the frequency domain. How do I remove zero frequency? Where is zero frequency? It's right there, right? If I want to remove that, then I could add in a negative impulse that would remove the frequency term. So if I Fourier transform back, this really was an unfortunate choice in hindsight. I'm going to have the rectangle again added to, what do I do with that impulse? What's the Fourier transform of an impulse? A constant. So, which is a little weird because I have a rectangle there that's already there. So how do I add a rectangle and a constant? Well, one way is to have the constant, if this is 0, make the filter longer. That makes sense. So the average is 0. And my constant has to be long relative to this rectangle. So I've made my digital filter much longer, but I can just as easily subtract off this constant. It's actually...
Why is the digital filter longer?
Yeah, let me give you another example. one that I like more.
How is the impulse removing the DC?
So the question, well, okay, let's go over this a little bit. I'll give you a better example in the next slide, but because this one's a little tricky. Because the time domain response is constant to begin with in the rectangle, and I'm subtracting off a constant, which would just give me 0, which would be nothing. So I have to make it longer such that the average of the digital filter is 0. Why would that matter? Because if it's average, let's say I had a constant term, a background term. If I have if I sum up every element in this digital filter and it equals 0, and I multiply that by the DC, it removes the DC. Should I say that one more time? Okay. Let's say I have signal that is varying in time quickly relative to the dimensions of the filter, and background noise that is constant over the length scale of the filter that I want to remove. If I have the constant term, if the signal is oscillating, it will be retained by the rectangle part. If the background noise is constant, then I'm going to have an equal number of negative and positive values. When I sum them together, it will be 0. Yes?
I don't know if this was like a couple weeks ago when you just like take your function and you move it down.
That's exactly the same process that we considered in that example. I'm going to give you one that's a little clearer. We're going to think about this same process. We're going to build a bandpass filter. And we're going to do it in 2 steps. First step is going to be a low-pass filter, and then the second step, I bet you can guess it, is a high-pass filter to remove the DC. So a low-pass filter, what would that look like in the frequency domain? You'd want to retain all frequencies up to some cutoff. Yeah. Actually, the width of that is f0, so that's f0 over 2, negative f0 over 2. This would be a frequency domain to remove the high frequency. And what would this look like in the time domain? We already know the Fourier transform of a rectangle is a sink, right? So then the digital filter is a sink. And this is called a Brickwall filter. It's called that because it stops abruptly in the frequency domain. I got nothing, no idea why it's a brick wall, except you hit it with your frequencies. Okay, so that would be our low pass. That's our that's our low pass filter. Yes. Because we're accepting all frequencies from 0 to f0 over 2, plus or minus. What about the high-pass filter? High-pass filter to remove low-frequency content. Well, we've already worked this one through, right? That is adding on to this something to remove zero frequency. And that would look like a offset sink. Just like we had an offset rectangle. Okay, any questions on this so far? The next question for you then, we'll keep these, is how long do you make your filter and what do they look like? Let's just do a quick survey of some of the different kinds of filters that are routinely used. Oh yeah, we'll do the interference one too. I forgot about that one. That's a good one. So this is the rolling average. And talk about the mechanics too. So the Brickwall filter, I think it's useful to sort of see what these things do in practice to sort of get to know what an appropriate filter might be. The Brickwall filter does a good job of reducing distortion and suppressing low frequency noise, but you really see this ringing here is all from the remaining noise that's still present. And it's quite obvious where it sort of abruptly stops and you have this frequency content. This ringing is pretty clear. If you make that longer, then you can do a very good job of suppressing it. And the goal for the digital filters that are illustrated in the lecture notes, there's two of them. Increase signal to noise, minimize distortion. You can never do both perfectly, because there's always frequency content of your signal that overlaps with the frequency content of your noise. And if you remove all of the frequency content of your noise at that frequency, you're also removing content of your signal at that frequency. So that's where this striking a balance comes in. Interference noise. Let's say you've got a digital filter and you've got 60 hertz line noise. I think it came up earlier as a common interferent. How do you remove 60 hertz line noise? If it's Now, you have to be careful because there's signal content at 60 hertz as well that goes away as soon as you remove the line noise. But to do this, you would have a remove one frequency. So what would that look like in the Fourier domain? Well, an impulse removed zero frequency. Let's say I want to remove a frequency F0. Yeah, there's two ways we can make offset impulses. Let's do the even one. I'm sorry? Yeah. Well, you're thinking Fourier transformed already. If I want to remove a frequency, then the way to do it, oh, come on, it's in here somewhere. Remove one frequency. There's a couple of clever ways to do it. The first is to have a rectangle, for example, in the Fourier domain. Let's just write on here. In that look like that would do the trick. What that would do is remove this frequency from the signal. And how would you get this? You'd take this waveform and Fourier transform it and then convolve. What would it look like in terms of its Fourier transform? It'd be a sinc multiplied by a sine, cosine. Or you can be really clever, because if you think about the sinc function, it has nodes, right? And if you put the nodes at the location, if we think this is one way to do it, and this would certainly work, but in this particular example, it was done the other way around. Chose a spectral sinc. So if you have a spectral sinc function, then the nodes where it crosses zero are gone. And then if you Fourier transform that, you have a rectangle, but that rectangle has a cutoff at that frequency. So the sink and the nodes in the frequency domain with the cutoff at the termini of the rectangle, Fourier transformed, will result in removal of those frequencies. In other words, the way to think about it is if you're only ever sampling at the peak, and if you're sampling over a period equal to the period of the interference, then the interference doesn't contribute. It contributes. I'm not explaining it very well, am I? Here, let me get another blank slide and show this a little more clearly. So we have two routes for suppressing this. Let's go with the sink route. Yeah, it's F0 over 2, because F0 is the period. Okay, so if I Fourier transform this, it will remove F0, this in the frequency domain removes F0 over 2 when multiplied, right? So the digital filter for this would correspond to a rectangle with a width equal to the period of the interference. So let's say I have something, I have that interference noise. If I take a rectangle that is exactly equal to the period, and if I convolve with that, what do I get? Well, I'm always integrating over one period of a cosine, right? So it goes from peak to peak with a valley in between. And so the integral of a cosine from 0 to 2 pi is 0. So by choosing the width equal to the period of the temporal interference, then we remove it. And conceptually, we could understand that in terms of multiplication in the frequency domain by the sink. Now, it's not the only way to do it. In fact, it might not even be the best way to do it, because not only does it remove this frequency, but it also removes all the higher harmonics. Okay. I think I'd like to end on a word on notation. There's a really nice MathCAD file accessible from the web page that provides a template for digital filtering. I think I do not want to go into the next topic, which will be polynomial fitting. Fitting to, it's really cool. What we're going to do is basically fit a data set. We'll do a linear fit of a data set to a polynomial expression. And that will give us a Savitsky-Golay digital filter, if you're familiar with that. If you've ever heard of it. If you've never heard of it, then that's okay. If you have heard of it, then that's great. That'll be the next topic. But I do want to sort of just touch base with respect to the mechanics, because there's some nice demonstration and illustration of that both in the lecture notes and in the demos provided. And it's basically coming down to the notation here. So we're going to have a data set of length d. That may be here, it's shown for a case of 20, but that could be typically 10,000 data points. It could be very long. That's your raw data set. And your filter is length f. Of course, the actual number of elements in your filter is going to be f plus 1, big F. And so we can think conceptually of this digital filtering by taking the filter and considering that element as we apply the filter, multiply and sum all the different elements in the filter. and then slide that along one time point at a time. And a couple of comments. There's a normalization constant in here. Why? Well, there's actually two comments about the normalization constant. First of all, it doesn't always work. Second of all, when it does, it always equals 1. And the reason for having this always equal 1 is that you don't want to rescale your data, right? If you have this equal something other than 1, then by the time you pass through and convolve it with this, you've changed the amplitude. The reason it doesn't always work is if you're trying to remove zero frequency, then you have to have an average value of 0. And so you can't have a norm that equals 1. So that's the one time it's sort of a pain, trying to come up with a normalization constant for something that doesn't, that removes the zero frequency terms. But for everything else, we want to normalize, and you normalize, in the case of the rolling average, what did we do? We took the same number, 5 places, and divided by 5. And if we add all of those up, we get 1. So we intuitively did this already. It's just the same idea generalized as we saw for the average. Okay. Anything else? All right. In that case, we'll pick up Savitsky Golay and talk about the exam on Thursday. I'll see you then.
Question.
Hold on just a second.